Here we're going to look at an interesting identity which was found in Ramanujan's fourth notebook. And in that notebook, it was known as problem number 723, and it was actually submitted to an Indian mathematics journal. Okay, so let's look at the statement. So we want to show for all natural numbers n, we have the floor of the square root of n plus 1 plus the square root of n is the same thing as the floor of the square root of 4n plus 2. So I think this is a pretty fascinating identity. Okay, so let's see how we can get started. So the first thing that we're going to do is take our n and write it as a bit more than a perfect square. In other words, let's write our little n as capital N squared. So that's a perfect square natural number plus m. And then m is going to lie bigger than or equal to 0. So if it's equal to 0, then n itself is a perfect square, and that perfect square is capital N squared. And then it is strictly less than 2n plus 1. So notice if it were equal to 2n plus 1, we could factor the right-hand side as n plus 1 quantity squared, and that would be the next perfect square, but we don't want to allow that. So let's notice that this allows us to set up a number line. So let's go ahead and draw that number line. And on the far left, I'm going to write the number capital N, and then on the far right, I'll write the number capital N plus 1. And so this structure right here, the fact that little n is equal to capital N squared plus m, that tells us that the square root of n is somewhere in between capital N and capital N plus 1. Okay, great. And now the next thing that we want to notice is we have two other numbers that are related to the square root of n that are helpful for this expression that are also between capital N and capital N plus 1. And so one of them is the square root of n plus 1/2. And that one may not seem super useful, but notice if we take a 4 out of this thing right here, we have n plus half, so that is pretty useful. And then the other one is the square root of n plus 1. And now by this construction up here, let's see exactly where these three numbers live. So we have capital N is less than or equal to the square root of n, which is strictly less than n plus 1. So that follows by our definition of capital N right here. And then next, we have capital N is strictly less than the square root of n plus half, which is also strictly less than capital N plus 1. Great, and that's because any non-integer rational number cannot have a square root, which is a natural number, which is what we would get if we had equal signs on each of those. And then finally, we have capital N is strictly less than the square root of n plus 1, which is less than or equal to capital N plus 1. So given these three inequalities, we can introduce three new numbers that are between 0 and 1 that will allow us to rewrite this goal equation, which I've called red star. And so let's go ahead and say, let's take A, B, and C. So those are going to be between 0 and 1, such that little n is equal to capital N plus a quantity squared. And so that possibility follows from this inequality. And again, because of this inequality, we know that A is in the half open interval 0 to 1, where we include 0. So it's equal to 0 if we have an equality right here. And now we can do the same thing for n plus half and n plus 1. So notice that n plus half can be rewritten as capital N plus b quantity squared. And now b is in the open interval because I don't have any equality here. And then finally, n plus 1 can be written as capital N plus c quantity squared. And now c is also in a half open interval, but now we include the top part. And so notice if c is equal to 1, that corresponds to equality at the top end of this. So now let's see what happens to our goal equation if we make these substitutions. So let's go ahead and write that down. So into red star. So let's first of all look at the left-hand side. So we have the floor of the square root of n plus 1 plus the square root of n. So if we substitute n plus 1 for capital N plus c squared, then we can take that square root, and the left-hand side looks like n plus c plus n plus a. So that's because we have the square root of n plus 1. So the square root of n plus 1 now is capital N plus c. And then we have the square root of n. So that's n plus a. So notice that simplifies. So that simplifies to the floor of 2n plus a plus c. Great. And now let's go ahead and see what happens to the right-hand side. So notice this right-hand side can be rewritten as the square root of 4 times the quantity n plus half, which is equal to 2 times the square root of n plus half if we factor that 4 out of the square root. So we'll take advantage of this. And so that means we can rewrite the right-hand side as the floor of 2 times the square root of n plus half, but that's going to be n plus b. So now we can distribute that a little bit, and that's going to give us 2 times n plus 2 times b. So our goal equation is equivalent to this equality right here. Okay, great. But now we know that capital N is a natural number. So we know that our goal equation holds if and only if a plus c equals 2b after having taken the floor, obviously. So that leaves us with our goal equation is equivalent to saying that the floor of a plus c equals the floor of 2b. Okay, so I'll go ahead and clean up the board. I'll bring everything that we need to move on to the top, and then we'll keep going. So let's see where we are so far. So we assumed that we could write little n as capital N squared plus m. M was between 0, it was possible to be 0, up to 2n plus 1, but it could not be 2n plus 1. Then we rewrote little n as capital N plus a quantity squared. A was on the half open interval 0 to 1. We wrote n plus half as capital N plus b quantity squared. B was on the open interval 0 to 1. And we wrote n plus 1 as capital N plus c quantity squared. And c was on the half open interval 0 to 1. And then we showed that our goal equality involving the square root and these floors was equivalent to this equality right here having to do with our a, b, and c. And that is the floor of a plus c is equal to the floor of 2b. And now we're going to break this down into 3 cases depending on this number m. So the first case is if m is bigger than or equal to 0 but less than n. And the second case is if m is bigger than n but less than 2n plus 1. And then obviously the third case will be if m is equal to n. So these cases are pretty short, and they both rely on the same observation. And that observation has to do with what happens if we take n plus 1/2 quantity squared. So let's see, if we multiply that out, we're going to get n squared, and then we'll have half times n plus half times n, so that's going to be n. And then we'll have half times half, so that's going to be quarter. Great. But now since m is strictly less than n, that tells us that m plus 1 is less than or equal to n. But what that tells us is that n squared plus n plus 1/4 is going to be strictly bigger than n plus 1. But obviously n plus 1 is strictly bigger than n plus half, which is strictly bigger than n. So in other words, this n plus half squared is bigger than n plus 1, n plus half, and n. But what that tells us is that a, b, and c are all strictly less than 1/2. So let's go ahead and write that down. So that means a, b, and c are between 0 and 1/2. Okay, but notice that means that a plus c is strictly less than 1, and 2b is also strictly less than 1. But now what that means is that the floor of a plus c is equal to 0, and the floor of 2b is also equal to 0. So that means in this case, we have proved the appropriate identity. Okay, so now let's move on to the second case. So we're still going to use this. So we have n plus half quantity squared. So that's going to be equal to n squared plus n plus 1/4. But now if m is strictly bigger than n, then we have this equality happening in the opposite direction. In other words, this is less than n, which is less than n plus half, which is less than n plus 1. But now this inequality tells us where a, b, and c are, and in this case, we know that a, b, and c are between 1/2 and 1. Great. But now since a, b, and c are between 1/2 and 1, we know a plus c is bigger than 1, but it's less than 2. And then we know that 2b is also bigger than 1, but less than 2. But putting those two things together, we see the floor of a plus c is equal to 1, and the floor of 2b is also equal to 1. So we have equality for our identity in this case as well. Okay, so good. We've taken care of case 1 and case 2. I'll clean this up and then we'll look at case 3. So now we're ready to look at our third and last case, and that's when little m equals n. And recall that little m was defined by this up here. We have n equals capital N squared plus m. So in other words, in this case, we have n equals capital N squared plus n. But notice that's the same thing as n times n plus 1. Great. And now we're going to look at this capital N plus half squared thing again, because now we can get another handle on what a, b, and c are in this case. So let's just recall that capital N plus 1/2 squared was equal to n squared plus n plus quarter. Great. But notice in this setup, that's equal to n plus 1/4. Great. But notice that n plus 1/4 lies exactly in between n and n plus 1/2. And so now we can argue the size of a, b, and c. And in fact, we can say that a must be less than 1/2. And then b and c have to be bigger than 1/2. Great. Again, that follows from this inequality right here, because n plus 1/2 squared is equal to n plus quarter, but that is less than n plus half and less than n plus 1, but it's greater than n. Great. But if b and c are bigger than 1/2, that tells us that the floor of 2b is equal to 1, which means our goal is we want to show that the floor of a plus c is equal to 1 as well, because that'll complete this identity. Okay, so now what we want to do is define two new numbers, which will be useful towards proving this. And those numbers are x and z. So let's define x and z by the following equations. So x is defined by the equation a equals 1/2 minus x. So obviously here x is the same thing as 1/2 minus a, but it'll be useful to write it like that. And then z is defined by c equals 1/2 plus z. So again, z is just c minus half, but again, it'll be useful to write it like that. So now I want to rewrite the floor of a plus c, which is our goal, using these new variables x and z. So we have the floor of a plus c now is equal to the floor of 1/2 minus x plus 1/2 plus z, which is equal to the floor of 1 plus the quantity z minus x. Okay, and now let's notice that this is equal to 1 if and only if the floor of z minus x is equal to 0. But the floor of z minus x is equal to 0 if and only if x is less than z. Great. And so what we've done is we have replaced this condition up here with our new condition, which is x is less than z. Okay, so we'll keep this new condition. I'll clean up the board and then we'll keep going. So now what we want to do is look at some equations defined by little n and little n plus 1 in terms of those squares, and notice that that will take us towards the end. So first of all, we can write little n as n squared plus m, but let's recall that m was equal to n. So in other words, we can write capital N squared plus n equals little n. But now little n was equal to capital N plus a quantity squared. But notice that a is equal to 1/2 minus x quantity squared. So that's one thing that we have. And then we'll do the same kind of thing for n plus 1. And we can write that in the following way. We have capital N squared plus n plus 1. So notice that's the same thing as n plus 1. But n plus 1 is the same thing as n plus c squared, but c is 1/2 plus z. So we can write capital N plus 1/2 plus c quantity squared. Now the next thing that I want to do is multiply these right-hand sides out on each of these. So let's see what we get for that. So I'll just bring this down. We have capital N squared plus n. And then over here, I'll leave it to you guys to check this carefully, but what we will have is capital N squared plus 1/4 plus x squared. So that's what we get from squaring everything. And then we have plus n times half, and then times 2, because we'll get 2 copies of that, so that'll be plus n. And then we'll get n plus negative x times 2. Again, we'll have 2 copies of that, so that'll be minus 2nx. And then we'll have half times negative x, and then we'll have 2 copies of that as well, so that's going to be minus x. Okay, so now let's notice that this guy will cancel with this guy, and this guy will cancel with this guy, and that's going to leave us with x squared minus the quantity 2n plus 1 times x. So I'm getting that from this term right here. And then plus 1/4 equals 0. So again, I just kind of flipped the sides of my equality here. Now we're going to do the same kind of thing over on this side of the equation. So I'll just bring this down. We have capital N squared plus n plus 1. And then I'll multiply that out. So I'll get capital N squared plus 1/4 plus, this should have been a z squared. And then I'll have the same kind of thing. So half times n and then twice that. So that'll be plus n. Half times z and twice that. So that'll be plus z. And then n times z and then twice that. So that'll be 2nz. Great. And now notice some stuff cancels. So this n squared cancels this n squared. This n cancels this n. And now we can take this 1 and move it to this side of the equation if we end up with a minus 3/4. So let's see what that gives us. That's going to give us z squared plus 2n plus 1 times z minus 3/4 equals 0. Okay, fantastic. So that's a good place to stop that. I'll erase this bit, bring this up here, and we'll finish it off. So let's see where we are. In our case, when m was equal to n, we earlier described why a was between 0 and 1/2, and c was also between 0 and 1/2. Then we introduced 2 new variables, x and z, that were defined by a equals half minus x and c equals half plus z. And notice that these inequalities imply that x and z are both less than half. And notice that our goal identity here, which was the floor of a plus c equals the floor of 2b, is now equivalent to x is less than z. And notice this whole thing is equivalent to showing our goal identity over here. Okay, and then also notice that we constructed these following quadratic equations for x and z. Okay, so now what I want to do is add these 2 quadratic equations and see what we get. So notice we'll have x squared plus z squared. And then notice we have 2n plus 1 are both coefficients of this. This one contains a minus sign. So we can write this as the quantity 2n plus 1 times z minus x. If we add those, and now we have minus 3/4 plus 1/2. So that's going to be minus 1/2 equals 0. So we put these 2 equations together into one equation like that. And now the next thing that I want to do is rearrange this thing a little bit. So I'll move this x squared plus z squared and this minus half to the right-hand side of the equation. So that'll give me 2n plus 1 times z minus x equals 1/2 minus the quantity x squared plus z squared. Okay, great. But now the important thing to notice is that x and z are both less than 1/2. But what that tells us is that x squared and z squared are both less than 1/4. So now that means that x squared plus z squared is less than 1/2, but it must be bigger than 0. So we're taking 1/2 and we're subtracting a number that's between 0 and 1/2, but that means that the right-hand side of this equation is positive. So look at what we have. We have 2n plus 1 times z minus x is positive. 2n plus 1 is always positive. So that means that z minus x, in this case, is also positive, which tells us that z is greater than x, but that's exactly what we wanted to show. So let's see what we've got. We've got z is greater than x, but that shows us that a plus c floor is the same thing as 2b floor, but that's the same thing as showing that the floor of the square root of n plus 1 plus the square root of n is equal to the floor of the square root of 4n plus 2 in this third case, where m was equal to n. Great, and that's a good place to stop.